Hello, my name is Julian Scott, and I am the Riparian Wetland AIM Data Manager with the Bureau of Land Management National Operations Center. The following presentation will cover methods for collecting data on hydrology and surface water characteristics within the riparian wetland monitoring plots. You can follow along in sections 5.3 of the Field Protocol for Lentic Riparian and Wetland Systems. Hydrology refers to the timing and extent of inundation or soil saturation and is the driving factor that creates and maintains riparian and wetland areas. Landscape position, climate, topography, surrounding land use, and soil permeability all influence the hydrology of these areas. Hydrology is the defining feature of riparian and wetland ecosystems. The hydrology of a riparian or wetland area is largely responsible for its vegetation composition. Wetlands are flooded or saturated for at least 15 consecutive days during the growing season and often much longer. Riparian areas can be drier but are still connected to and influenced by surface water bodies. The hydrology of a site influences plant communities and favors those species that are adapted to the specific patterns of flooding or saturation found at that site. Hydrology also influences biologic activity in the soil. Soil saturation leads to anaerobic conditions in which soil microbes must adapt to the absence of oxygen. Over time, this can lead to the formation of soil hydric indicators. In this figure, you can see the direction of water flow into and out of wetland systems. Inputs include groundwater flow, surface water inflow, and precipitation. Outflows include groundwater outflow, surface water outflow, and evapotranspiration. The position of a wetland on the landscape, the local climate, and the soil permeability of a given area all impact the movement and collection of water on the landscape. For instance, wetlands rarely form in areas with high slope and high soil permeability because water would not accumulate there. It would simply flow through. Here in this photo, you can see that the yellow arrow is pointing to an area where landscape position and soil permeability are not favorable for wetland formation to take place. The steep slope of the talus field combined with the high permeability of the substrate do not allow for sufficient water retention. The area in the foreground, however, indicated by the red arrow, is a much more conducive area for wetland formation to take place. Its position on the landscape allows groundwater and surface water inputs from the upland to collect, and its gentle slope is more capable of retaining those hydrologic inputs. Though hydrology is a critical characteristic of riparian or wetland areas, it can be difficult to characterize and measure in the field because hydrology is dynamic and variable. The Riparian and Wetland AIM protocol considers hydrology a covariate method, meaning that it's used to help characterize the site for purposes of classification, stratification, or a wetland's ecological potential. Hydrology information is collected in all riparian and wetland AIM monitoring plots. Data collected include evidence of surface or groundwater, dominant and supplemental water sources, characteristics of surface water if present, characteristics of the dominant channel if present, and a general hydrology description. The first step is to look for water on the plot. Look for evidence of current surface or groundwater, such as pools or channels of water or a high water table in the soil pit. Even if surface or groundwater are not observed, look for evidence of past inundation or saturation, such as aquatic invertebrates, drift deposits, drainage patterns, or soil cracks. Refer to Appendix K in the protocol for a list of hydrology indicators developed by the U.S. Army Corps of Engineers. Be sure to record observations using terminology consistent with the indicators where possible. At every riparian and wetland AIM monitoring plot, you will determine a dominant water source and record any additional sources. When determining the water sources influencing the site's hydrology, refer to a topographic map, historic imagery, and wetland classification information. Note that Appendix L in the protocol can help you decide if the wetland ecosystem is groundwater dependent. It's important to consider a range of factors, including landscape position and watershed setting, wetland types known to exist regionally and locally, nearby land use, local climate data, and existing information about the site. It is very important to walk the entire site when determining water sources. Next, we'll go through the water sources a little bit more. Generally speaking, water sources can be categorized into groundwater, surface water body, and precipitation sources. We will now discuss and define each major water source that could influence a site. The first set of water sources all fall under the groundwater category. They include regional groundwater, local floodplain groundwater, and seeps and springs. Regional groundwater influences many wetlands. This is groundwater originating from the larger landscape. Regional groundwater often occurs at the base of slopes or alluvial fans, where regional aquifers discharge diffusely to the land surface. Subsurface geologic features, such as low permeability bedrock, can also push regional groundwater flow to the surface. Local floodplain groundwater is shallow and hydrologically connected to a stream channel through unconsolidated alluvial sediments. In many cases, riparian areas and floodplains have shallow, plant-available groundwater where groundwater discharges to a stream channel, in this case called a gaining stream, or where stream recharges the groundwater system, called a losing stream. A seep or spring is a localized point of groundwater discharge. Use this water source to indicate a specific point source of groundwater discharge, such as a spring head. This water source can occur on its own or in conjunction with regional groundwater discharge. It may be tempting to record seep or spring as the dominant water source on sample plots named after adjacent springs, such as Coyote Spring or Willow Spring, but use the information you have gathered while sampling in the monitoring plot to help inform the most appropriate water source. The second set of water sources all fall under the same category of surface water. They include overbank flooding, stream inflow, ponds, lakes, and reservoirs, and estuarine or tidal flows. Overbank flooding is when water has escaped the banks of a stream or river. Riparian areas and floodplains adjacent to stream and river channels are often influenced by periodic overbank flooding. Sites with a hydrology dominated by overbank flooding include those with hydroperiods closely tied to flooding events, or systems like this one, where a beaver complex has impounded stream flow. In contrast to overbank flooding, stream inflow is reserved for terminal wetlands that receive inflow from streams rather than overbank flooding that flows through the site. In most cases, stream inflow spreads out, pools, and infiltrates across the wetland to maintain high water levels in the soil. High evaporation and salt precipitation is also likely in a terminal wetland. Wetlands with a hydrologic process dominated by a pond, lake, or reservoir have a direct connection to an open body of water. Riparian and wetland areas located along the margins of ponds, lakes, or reservoirs can be tied to rising and falling water levels via surface or groundwater. However, not all wetlands or ponds or lake margins are solely tied to open water bodies. Consider other sources like upslope groundwater discharge, fluvial and alluvial sources. Estuarine or tidally influenced riparian or wetland areas are located along a coast where the hydrology is connected to ocean water. Water levels may rise and fall with daily tidal fluctuations. Surface water in the riparian or wetland area may be as saline as ocean water or may be a mix of freshwater and ocean water. Freshwater inputs are often at deltas where streams join the ocean and wetlands form at the interface between the delta and the ocean. The third set of water sources are related to precipitation. They include direct precip, overland flow, and snowmelt. Wetlands dominated by direct precipitation are restricted to areas with high seasonal or annual precipitation. Very high amounts of precipitation can support bog wetlands, which are saturated wetlands isolated from groundwater sources. To assign this as a water source, consider whether direct precipitation is the wetland's predominant water source, not whether the wetland occasionally receives precipitation. Wetlands driven by precipitation are rare in the arid West, but common in Alaska. Wetlands fed by overland flow accumulate runoff from the upslope. Overland flow is the diffuse, downslope movement of water over land that occurs when precipitation exceeds the soil's infiltration capacity. Examples of overland flow include depressions like plaias or vernal pools that accumulate runoff after large rainfall events and often have low permeability soil or bedrock that collect and perch water from immediately adjacent areas. For these wetlands, precipitation is an indirect source rather than a direct source. Wetlands that rely on snowmelt are found in the upper montane to alpine zones where slowly melting glaciers, snowfields, or snowbanks provide a consistent water source in the spring and summer. Expect to only find these types of wetlands in higher elevation areas that receive significant snowfall. Some types of wetlands are fed by other water sources that don't fall under the groundwater, surface water, or precipitation categories. Wetlands are sometimes formed and maintained by excess irrigation water applied to farmlands. The excess water flows downslope and accumulates into drainages or other low points. Irrigation canals can also seep into the downslope side. In this example, you can see where excess irrigation water has collected in the drainages, flowing away from the adjacent agricultural fields. When thinking about water sources, it can be helpful to consider the physical setting of the wetland at the watershed scale. The position of a wetland on the landscape influences the source and movement of water within a wetland. For example, a wetland at the base of a mountain may receive regional groundwater discharge from the surrounding slopes and/or seasonal spring snowmelt. A riparian area in a valley bottom may be dominated by overbank flooding and/or local floodplain groundwater. In addition to landscape position, taking ecoregion into account can help to understand what hydrologic processes are typical of the greater area. For example, in the arid and semi-arid basins of Nevada, you can expect to find wetlands at the terminus of streams or fed by springs, while in the alluvial valley bottoms of the Colorado Plateau, you can expect to find wetlands sourced by local floodplain groundwater and overbank flooding. Surrounding land use, especially groundwater extraction, can influence the seasonality of a wetland. Irrigation practices, including stream diversion and groundwater pumping, can cause changes to wetland hydroperiod. In this plot, we have depth to water on the y-axis in centimeters and time covering October 2009 to October 2012 on the x-axis. This illustrates that wetlands adjacent to groundwater extraction activities may experience reduced water levels during the summer and increased water levels during the fall or winter, as shown in this figure. Be sure to review climate data and be familiar with the recent weather, particularly if there has been a recent precipitation event. Notably, the drought monitor for this spring shows that most of California, Oregon, Nevada, Montana, and Utah are in severe drought or worse. Expect the intensity of your monitoring area drought to increase throughout the course of the growing season. Once water sources are determined, record if surface water is present within the monitoring plot. If surface water is observed, estimate the extent within the plot, the predominant depth across the entire monitoring plot, and the distribution of surface water, meaning whether the water is concentrated in one water body like a channel or pond, occurs in many small patches, or as shallow standing water. In addition, observe and record several characteristics of the surface water, including characteristics of the water surface, such as oily sheens or algal blooms, the smell of the water, and the substrate below the surface water body. Further guidance on these characteristics can be found in section 5.3 of the Riparian and Wetland Aim Protocol. If a channel flows through the monitoring plot, you will need to record its characteristics. If there are multiple channels within the plot, take measurements on the widest dominant channel. Measurements include channel length, including meanders, average channel width, average channel depth, and the depth of water within the channel. In addition, note whether the channel dimensions were clear and well defined. Channel length measurements can be checked in a GIS in the office with aerial imagery. If variable width and depth measurements should be taken at up to 5 locations and averaged. As the figure shows, channel width and depth measurements of the channel itself are independent of any water present in the channel. Rather, measure from the top lip of the channel. Depth measurements should be made to the deepest part of the channel. The water level may be above or below the top lip of the channel at the time of sampling. After recording the data in the iPad, take a minimum of 2 photos of all dominant channels observed within the plot during the site visit. Additional details about the number and characteristics of small channels within the plot should be included in the general hydrology description. Here are some examples of channels found in wetland and riparian areas. Pictured on the top left is an example of a small rivulet. On the right is an example of a stable stream. At the bottom left is a site that may not have a well-defined channel formation. Measurements in this case might be estimated, and the lack of clear edges noted in the comments. At each site, you will need to take notes on the general hydrology of the sample plot. Make objective observations and take notes on anything that may impact the hydrology of the site. Include any overall notes on site hydrology, including inflows, outflows, seasonality, surface water patterns, wetland hydrology indicators, channels, and any hydrologic disturbance. Finally, take overview photos illustrating the extent and distribution of surface water, as well as photos of the features noted in the description of the hydrology site, including head cuts, rills, channels, berms, deeply dug pits, or sediment deposition. Record photo numbers and a short written explanation in the photo log datasheet. The photos pictured here represent various hydrologic features of interest. Starting from the top left and moving right, a head cut and resulting plunge pool along a small montane stream, a canal, a spring snail, which is a species of interest in many field offices, evidence of recent beaver activity, and on the bottom row, an excavator and a recent dredge pile, and a head cut erosional feature in an area of diffuse groundwater. This concludes the hydrology overview and methods following the Riparian and Wetland Aim Protocol. For additional guidance on the hydrology methods, please refer to section 5.3 of the protocol.